So, in the last class, we talked about backpropagation in CNN. So, that basically covers everything we need to know about convolution neural networks. Well, maybe just the basics of it. But today, what we will try to understand is the problems that we have with neural networks. So, one of the problems that we have is overfitting. So, why this? So what happens is you need to understand, as you are increasing the neural network, the number of layers keep increasing, the number of neurons keep increasing, even in CNN. Now this time, instead of using one weight per neuron, we are using one particular filter. It might have a lot of let's say a lot of numbers and everything. So what I mean to say basically is the number of trainable parameters keep increasing. So this might be some of the reason that causes overfitting, and it can be a very big problem. So what happens in neural networks is there are a few things or tricks that we can do to actually avoid overfitting. So what does that mean? So well, there are a few things that can avoid overfitting. Today we will learn about that. So we have a few techniques that we can use to avoid overfitting. Some of these are, well, number one we can start with is batch normalization. Then what we can use is dropout. We have weight initializers that we use. Remember, those are also kind of the techniques that can be used to avoid overfitting. So these are basically regularizers or things that are used to regularize. Weight initializers, they can also be known as kernel initializers, obviously. And the final thing that we have is known as early stopping. So first let us talk a bit about overfitting. So what basically overfitting means? So overfitting is basically when your model works very good on the training data, so that your accuracy is very high on the training data and the loss is very low in the training data, but it does not perform that well on test data. So you might understand that through graphs and stuff you can see the training loss is decreasing. However, at some point you see that the test loss or validation loss does not keep decreasing anymore. So in those cases you can understand, okay, so this is not working well. So those are one of the reasons, or I mean that is what basically overfitting means. Now what we will understand is we will go through each of these one by one and I'll explain everything to you. Okay, so first we start with batch normalization. So this was basically the diagram or basically the equations that were given when you read over the paper about batch normalization. So batch normalization, what it basically is when you are inputting data, right? So you can input one data might be very different from another data. So let's say you have a white dog here, right? So you have a picture of a white dog, you are doing some classification. So this is in the training. So let's say your model is totally trained on white dogs, but you get a black dog here. So in that case, in the testing thing, you need to understand is the distribution for white dog is going to be very different from the, not very different, but at least a bit different from black dogs. So in that case, since the distributions are different, we will require something so that despite the color or despite the difference in distribution, our model still is able to work. So batch normalization, what it basically does is it keeps different values in or different batches in a particular distribution so that you do not get deflected from that. Okay, so now let us look into the formula. So here we have some labels. Okay, we don't have to understand everything, but yeah, batch normalization basically means when you are inputting data, you always input it in batches. You might have learnt about mini batch and gradient and mini batch, gradient descent and batch gradient descent and everything. So what batch normalization basically means is when you input the data or you feed the data into the model, you feed it in batches, so you can normalize that every time. And also batch normalization is basically a layer in Keras, so you can use this even after some other different layers, dense layers. So usually we use batch normalization in the middle after a convolution layer or after a max pooling layer. So that basically helps is even when you output the value, the output can be very different from distributions. So batch normalization basically helps to normalize and keep them within the same distribution so that you get more accurate results. Also, it has been seen that batch normalization helps in converging data, so you can get to the results faster. So that is one of the very good things about batch normalization. Okay, now let us talk about how this works. As you know, normalization, it is basically batch normalization is basically normalization. So whatever values you input, those values will be normalized. Okay, so here is what happens. So first you find the mean of all the values in the batch. Okay, so let's say I am using a batch from x1 to xm, right? So there are m values. So what I'll do is I'll first of all find the mean of that value. So mu is basically the mean. Then I find the variance. Well, basically it is used to find the standard deviation, but yeah, so you find the variance. Then once you find the batch mean and variance, you can normalize it. So it's basically what is doing is, the whole thing about batch normalization is you have a batch and you normalize the whole thing, but it does not end here. You need to understand, even after normalizing, you have to scale and shift it. So why is that important is, let's say you have a dog. Okay, so your image, you have a dog, but it has a very big close-up shot of a dog, so dog occupies most of the part of the image. But at the same time you have another picture, but the dog is a very little part of it. So in that case, what will happen is, if you scale and shift, it is invariant to those, so it can be used to identify both. It will actually be able to identify both. So then use the scale and shift. So what it means is, we'll be multiplying a gamma value. This is obviously a trainable parameter, gamma value with a normalized value, and add a beta to it. Again, beta and gamma are trainable parameters. So this is how batch normalization basically works. So what are the pros and cons of batch normalization? Let us talk about that. So batch norm, what it basically does is, it helps in converging. So whenever you input data or feed into the model, you are feeding it in batches. So here you have a batch of 4, and I usually said that when we are feeding the data, we usually feed it in 2 to the power n value something. So it has to be in this form. So we feed the data in batches, and each time we can normalize the batch. So this helps us so that our data remains in the same distribution, and it can even handle 10 different distributions. So that is why batch normalization is used. Next we will talk about something known as dropout. So dropout is one of the early stage discoveries, and this was basically used to actually understand and regularize the input more. So what that means is, even when you were, I suppose, studying, you might have heard about L1 and L2 regularizations, right? So dropout is also one of the regularizations. Okay, so what dropout basically means is, here is a very good diagram. Now this diagram is taken from the paper itself. Okay, so they have given this diagram. So for every dropout, you have a dropout value. Okay, so what happens is, you have this as a standard neural network. This is a multi-layered perceptron. You can also use this in CNN, but yeah, this is a multi-layered perceptron. So what happens is, here, since all of this is very connected, it takes first of all a lot of time, number one. Number two, you can have a problem of overfitting. Like I said, you increase the number of weights, you increase the number of neurons, there is a big chance that you might overfit the whole data. So that is why we have this whole thing. But in dropout value, suppose you have a dropout value of 0.2. So what that means is, randomly from all the layers, 20% of the neurons will be removed. So the rest will be used to calculate the whole thing. Here you can see this is a standard neural network. Here I applied, so let's say here you have a 50% dropout rate. Okay, so here 1 2 3 4 5, so 50% of 5 will be removed. So here 2 got removed, here 3 got removed, here again 2 got removed. So for every training epoch, in fact, so for every epoch these number of neurons will keep changing. So now this is removed. In the next epoch what will happen, maybe this is there and everything connected to this is there, but this gets removed, right? So randomly 20% or whatever the dropout rate you might select might get removed. So what this helps is, it helps in thinning out of layers. So this is basically called as thinning out layers. So the layers have been thinned out, that means random neurons have been removed. So why is this useful? So what happens with thinning out is, at any point of time very few neurons are active. Less neurons means chances of overfitting are less, because the data is, see, sometimes it might happen that the data is less but your trainable parameters are a lot. So in that case it is good to use dropout, and it has been shown through results. Obviously if you go through the paper of the whole dropout, you will know that it has shown results that dropout actually helps in increasing accuracy. This was one of the early things that were used. The reason why is, see, this is not a very standard neural network. You have to add more neurons to it, you have to increase the number of layers. So as the number of layers go on increasing, the chances of overfitting also increase. So there is a time when it happens is that the number of neurons are, the number of layers are a lot, but you are not able to get more accuracy. What people say is, if you have more depth you have more accuracy, but there comes a point where this does not happen. This is because you have the problem of overfitting. And to solve that problem, we have dropout. So you have a dropout value, and according to that dropout value, random neurons, that percentage of random neurons will be removed from each layer. Okay, and now let us talk about the final one, that is early stopping. So early stopping is basically nothing. What early stopping basically does is, see, let's say I am running a model, okay, and I have run that for 300 epochs, but in the mid of this thing, and when I'm running and when I'm seeing the whole data that shows written how much improvement is done, what is the test loss, training loss and everything, so I am seeing that my loss is not decreasing anymore and my accuracy is not increasing. And let's say this is about some 150th epoch, and here I have my training, this is the loss, and the loss is here, and it is not increasing after this. So there is no use in running it or exhausting my resources, resources of wherever I am running, my time and everything for 300 epochs, when I can easily stop it here. So what early stopping basically does is, now this also helps in overfitting of data, obviously. So what this does is, early stopping means is, there are a lot of metrics in early stopping, but one of the things is you can decide how much you want to, where you want to stop. So I can say, let's say when my loss, when the difference between the previous loss is stagnant or something like that. So how can you find where your loss is stagnant? Well, there is one thing that you can do is, you can say that when the previous epoch minus the recent epoch, let's say, the difference is close to 0 or something like that. So you can actually fit in a factor, and you can say, okay, if let's say my loss is 0.005, okay, so if my loss is greater than this, I'll keep going. If the loss gets less than this, okay, then I'll stop. And if this is lost for more than 2 or 3 epochs, so that is known as patience. So what patience is basically like 2 or 3 epochs. For the last 2 or 3 epochs, the difference in the losses is this little. So if the difference is this little, why should I waste my time running it for even more epochs when I know I can have the chance of overfitting? So in that case, we can use early stopping and stop the whole thing. And finally, obviously, you also have weight initializers. Now, nothing new here, obviously. You have learned about weight initializers. So they also basically keep a check on overfitting. This is also a regularizer. So what are basically initializers? Hey, normal, glorot, and different things. So what they basically do is initialize the weight, and they are also a kind of regularizer. Okay, so let's revise back one more time. What are the different techniques to avoid overfitting? First of all, why overfitting? So overfitting basically happens when you have a lot number of training parameters, and that can cause a lot of problems. Okay, so that is why we have overfitting. So to solve this problem, we have regularizers, different types of regularization techniques. So what are some of the regularization techniques we talked about? We have batch normalization. So batch normalization is basically what? You feed the data into the model in batches. So the batches can be normalized before feeding. Okay, even in the middle of training or in the middle of 2 layers, you can add a batch normalization layer. So what batch normalization will do in that case? So whatever output has been given from the previous layer after convolving or finding the weights and everything, you can batch normalize it, because sometimes it may happen that they can give a different distribution. So for different batches, you can have a different distribution. Hence batch normalization is important, and this helps in faster converging. Next we have dropout. So when do we use dropouts? Dropouts are basically used to remove some neurons. So you have this, and it will help in removing some neurons. You have a dropout value. Once you give that value, that percentage of neurons will be removed. Okay, so after dropping out, what happens is, in dropping out, it helps in better accuracy. Then what did we talk about? We talked about weight initializer, sorry. So why do we need weight initializers? So weight initializers also help keep record or act as a regularization technique to prevent overfitting. And we talked about weight initializers earlier itself. We had glorot, and we had hay and normal initializations. Yeah, you might remember everything. And the final one is early stopping. So why use early stopping? To prevent the use of resources and to not have a chance of overfitting. Okay, so that is basically the whole thing about overfitting, and these techniques are actually going to be used a lot. Okay, so be careful and understand these properly, and that's it for today. In the next class, what will happen is, we have learnt about a basic CNN architecture, we learnt about pooling, and we learnt about how backpropagation works, and now we have learnt about different techniques to avoid overfitting. So in the next class, what we will do is, we will understand the different case studies of CNN. So what that means is, there have been actually neural networks, neural models that have been tested out, and those models work better than other models. So we will be studying about those models in detail, and believe me, there are a lot of models, and most questions about convolution neural networks actually come through those models. So it is very important to understand this properly. Okay, so that's it for today. Thank you and keep learning.